I was interrupted, and that's why I had to stop mid question. And also I realized that I was doing something dumb. So they said concave mirror. I thought concave lens. That's not what they did. So a concave mirror is placed on a horizontal surface, and two thin uniform layers of different transparent liquids are formed on the reflecting surface. So two thin layers, different transparent. Okay, so fine, something like this, huh? And then there are liquids, so I will say, okay, maybe they are just straight surfaces. So you have this and that, right? Okay, and these are both uniform layers, whatever. And the surface, sorry, the refractive index of the upper and lower liquids are mu1 and mu2. So this is mu1 and this thing is mu2, right? The bright point source at a height h, d is very large compared to the thickness of the film. Yeah, whatever. So right, that's d. Okay. About the mirror coincides with its own image. Oh, that's important, I guess. Right. Um, the radius of the curvature of the reflecting surfaces therefore is. Oh yeah. So let's do it. Let's do it. The final index of the thing will just be negative. So negative 1 upon v, and then initially the index was 1. So negative 1 upon u is equal to. So first surface, you are going from 1 to mu1. So mu1 is 1, but that upon the radius of curvature, which is goes to infinity, huh? So that's 0. Oh, nice. And then the other surface as well just has 0. And then you're going from mu2 to negative mu2 with a radius of curvature r over here. Yes. Yes. So it's like negative 2 mu2 upon r. Yeah. Right. Then you are going back once again 0, then once again 0. So this is the whole thing. That's our formula for this kind of system. Yes. Now you are saying u is just negative d. So you got uh, negative 1 upon v plus 1 upon d is equal to negative 2 mu2 upon r. The r is assigned. And in fact, you know what, like, okay, just say this thing is the positive x-axis, then r will just be negative r. So yeah, just right. And now this is the unsigned quantity. So there we go. And v is also just negative d, which is, yeah. So because of that, it's got 2 upon d is equal to 2 mu2 upon r. And there we go. You got the radius of curvature. It should be mu2 times d. So, right. Wait, they are saying upper and lower liquids are mu1 and mu2 respectively, right? So this is mu1, this is mu2. Of course, it's going to be then mu2d, right? So 33 d. Okay, 34. The dispersive powers of two lenses are, oh come on, like this. I don't like this. Are 0.01 and 0.0. Focal length of one of these is so what was the dispersive power once again? So yeah, for each of these different wavelengths, you have a different focus, right? Yeah. Okay, I don't remember what the dispersive power was. It's like, okay, it's the change in the focal length of the, right, so the change in focal length is just like from red to violet, whatever the focal length, how much it changes, and that thing upon, because yeah, as your wavelengths get shorter, your refraction becomes much larger, and that's why f violet minus f red, and that upon f yellow, right? That was the refractive what, sorry, that was the dispersive power, right? Yeah. Huh. So right, that's the way it was defined, I think. Of course, that must have been a thing. Oh, and because it was actually like h upon f was the angular dispersion and stuff, right? No, h upon f was the deviation, I guess. So, oh yeah, h upon f red and then f yellow, something like that. Yeah, so that will give us the angular dispersion. Right, right. sorry, f violet and f red. That's how it's got to be. You get the idea, right? It's just f, so it's like delta f upon f yellow. That's what it is essentially. Okay, so that's the way it was defined, I think. Okay, so once again, just write that down. Our dispersive power is the focal length of violet minus focal length of red upon focal length of yellow. So dispersive powers of these two lenses are 0.01 and 0.02. If the focal length of one is plus 10, then what should the focal length of the other, so that they form an achromatic combination? What? Okay, I don't understand what we are dealing with right now. Ah, what? So they form an achromatic combination. So these just go back in. That's what you're saying. Uh, I don't know, right? This is, I didn't read this properly, and I'm not going to do this because I never seen this before. Why should I? 34th is not answering that. Or maybe like, I mean, okay, if these everyone are like taking that seriously, I should probably deal with this. But fine, I'll do this later when I'm done with this exercise. 35. Image formation from spherical mirrors. Only paraxial, okay, in image formation from spherical mirrors. Only paraxial rays are considered because they are easy to handle. Yeah, you could say so. Contain most of the intensity of the incident beam. Fine. I don't think that's correct, but whatever. Forms neatly nearly a point image of a point. So yeah. So C is the, I think it's the main reason. Shows minimum dispersion effect. Well, no, you can just use monochromatic light. What's the big deal? So C, I think, is the main thing. So 35th C. You know how I deal with it? So radius of curvature, right? We always call it radius of curvature, not the radius. Why? Because it's not actually supposed to be just spherical surfaces. It can be any kind of surface that can be approximated as a spherical surface for that local region, right? And the way we do it is that we take uh, what do we call it? What do we call? Yeah, we take a small aperture, right? So that the rays actually go to a single focus. That's, they look like they're going to a single focus. That's why we take that. So if we didn't do that, they would not go to the same point, right? And that would not form an image in that case, right? So that's why you have to take um, small aperture, right? And paraxial rays. Okay. In figure 1, the liquids L1, L2, L3 have refractive indices this. So therefore the arrangement corresponds to what? Oh, so where do we keep the object? Is like over here or over here? What's happening? These are all liquids, you say. So I don't get it. What do we do? Where are we keeping the object? So it will depend on where the object is. From which medium are we seeing the object? What's happening? You don't say all that stuff. Why? I mean, like, not like it really matters, because in the end, whether it's converging or not, that just depends on you know uh, the power thing, and not really on what the coefficients of final and initial, sorry, what the indexes of the final initial medium are. So yeah, you can just skip that. So what we'll do is just say, okay, like you have object over here in the space, so reflecting is 1, and then yeah, boom. So for this surface, just have mu2 minus mu1 upon r is equal to 0, because r approaches infinity. Similarly, for this flat surface, you don't have that over here, but for these two you do have it. So it's going to be this thing, L2. So okay, this is like mu2 minus mu1, that upon this guy's radius. And what are the radius of curvature? But okay, what are the radii curvature? Because without those, we don't know what to do, right? Okay, it's like R1 is positive, and then you got so negative 1 upon R2. I know that. But what we'll do is like, sorry, it should be positive 1 upon R2. What we'll do is just say that radius of curvature is like negative R2, right? For this other surface. So this will be minus mu3 minus mu2 upon R2, where R1 R2 are now signed, sorry, unsigned quantities, positive basically. Mu2 minus mu1 is just negative 0.05, so negative 0.05 upon R1, and then mu3 minus mu2 is okay, okay. So it just continuously decreasing, huh? Okay. Arrangement corresponds to biconvex lens, concave, convex. Without the curvature, we don't know. We don't know what to do. Should we go with the assumption that these radii are actually the same? So R and R, huh? I don't know. But mu3 minus mu2, that's just going to be. Oh, come on. This is so not good. It's negative 0.3, but we don't want to be negative. We want it to be positive so that we can see something for sure. But now we cannot. What is this? Why did this happen? Oh, okay. This is okay. Yeah. So this will be like plus 0.3 upon R2. Now at this point, we have to go with some assumption that R1 R2 must be the same. Otherwise, we cannot solve it. From the figure, it looks like these are the same. So yeah, this just becomes like 0.025 upon R is the big group. So the focal length is like positive. Huh? Yeah. So it's positive. So can it be a concavo-convex lens? Can it be a biconvex lens? Well, it doesn't look. Wait, what? What is this? Why would you want to do this kind of analogy? This would make no sense. There's no need for doing this. Because the first surface is having a negative so-called, okay, this might be called as 1 upon focal, like power. It has a negative power. You could say that. So, right, this would correspond to having, so what has negative power as negative focal length? Of course, it's supposed to be a concave lens. So the first is just a concave surface with the inside material having a greater index than 1, and then the next guy has posits, like it's something like this, huh? So it's a concavo-convex lens, yes, but that's a very weak analogy. It has different properties that come on, seriously, why would you want to classify it like that? Fine, if that's what you want to do it. It's a concavo-convex lens. The next one, yeah, so C is the way to go. So 36, 37, huh? 37 is a convergent beam of light is incident on a convex mirror of radius of curvature 60 centimeter as shown in the figure. The image formed by the convex mirror is convex mirror as shown. Oh, so these are just going to this point. What is this point? Okay, it's 10 centimeter. So it's a virtual object. Sorry, yeah, it's a virtual object of like 10 centimeter. Yes. Its radius of curvature is 60 centimeters, like its focal length is just 30. And it's positive as well, right? Yes. So image, yeah, let's do this thing. So 1 upon V plus 1 upon U. So U is this case is positive. Minus 1 upon 10, that's equal to 1 upon F. And then F is just 30, so 1 upon 30, there we go. Cool. 1 upon V is equal to 3 upon 30 plus 1 upon 4 upon 30, which is 2 upon 15. So it should be 7.5 centimeter, I guess, right? Positive. That means 7.5 centimeter behind the mirror. Yeah. And of course, it's virtual because what else could be happening? It cannot go actually behind, right? The rays cannot go behind the mirror. That would be weird. So virtual and 7.5 centimeter behind the mirror. 37th C. Yeah. Wait, no, okay, I messed up. It should be plus. What am I doing? What am I doing? It's the mirror formula, not the lens formula. 1 upon b is equal to negative 1 upon 10 plus 1 upon 30, which is negative 3 upon 30 plus 1 upon 30, which is negative 2 upon 30, like negative 1 upon 15. So it should be 15 centimeter in front of the mirror. Sorry. It's very real in that case because, yeah, possibly that's what's happening. Yeah, right. So these aren't at the center of curvature. These are actually aiming at some point before that. That just means the angle with the normal is like, yeah, it's gonna reflect and go like this. So it's going to be at some point like that. This is the real, I guess. So it's the real and 15 centimeter in front of the mirror. So it'll be section B. 39th. Sorry, 38. The following figure shows different arrangements of two identical pieces of plano convex lens. The refractive index of the liquid used is equal to that of the glass. Then the effective focal length in the three cases is, so look at this guy. Look at this. What is this? Yeah, I mean it's like glass and then once again glass and then once again glass. Come on, it's just a slab of glass basically. This has no focal length. Yeah, or you could say okay, it has because like okay, these have zero curvature. This has a focal length of infinity, right? That's one thing you could say. So you just send in parallel rays, well, they never converge. So you would say it's converging at infinity. So F3 is bigger than any of these. What? No, F3 is not zero. That's not right. What about F2? I don't think F. So it's got these two, huh? Well, F1 is just the convex lens. So F1 is, yeah. And then you got these. Well, if you think about it, these are just these two parts, but then rearranged. So this should also be having the same focal length as F1. So F1 is equal to F2, and then F3 is not zero. F3 is just infinity. Yes. Yeah. Isn't that correct? So then none of the above would be the thing. Well, we just have to check if F1 and F2 are going to be the same. So for F2, so first guy has no power, and then the second guy is going from mu to 1. So it's like 1 minus mu, and then you got, yeah, so the order is now different, and that's why, okay, it turns out the same thing, in fact. So it's like 1 minus mu, and that times of, sorry, that upon. So this guy's radius of is like negative r, and then you got plus mu minus 1 upon positive r, right? So it's like 2 times of mu minus 1 upon r, and then the last surface has 0 as its power thing. Yes, so 2 mu minus 1 upon r, that is the power of this guy, and then the power of this guy is also mu minus 1 times 1 upon r plus 1 upon, so yeah, minus minus plus. So this is the same thing. So F1 is equal to F2, of course. And then F3. F3 is like, it's supposed to be infinity, I guess, you know. Yeah. It's like, you send in parallel rays, they never converge. So what do you make of it? It must be converging at infinity. What else could be the thing? So that would be like saying, and what are they saying though? Okay, refractive index of the liquid used is equal to that of the glass. But that just means like a slab. Huh? But F1 must be at least equal to F2. F3 is equal to 0. That is not correct. I don't think that's correct. And then it's bigger than F3. Well, F3 is supposed to be infinity. Or you could take that as negative infinity or something. Oh god. Now what do I do with that? Is F3 equal to infinity or negative infinity? Does it even matter? Because we are talking about the... Okay, wait a second. I guess I'm gonna like say none of these, right? Even though I'm more inclined towards the C option. because it seems like, okay, f3 is going to negative infinity might also work, but honestly, it's just, yeah, it's like not defined actually. 39, okay, that's not, there's no 39, this is exercise 2 now. So, fine. And now we can do 34, I think. So, do 34. Yeah, what was 34? Again, dispersive power of two lenses are 0.01 and 0.02. If the focal length of one lens is plus 10 centimeter, then what should the focal length of the second lens so that they can form an achromatic combination? So now I know nothing about what dispersive powers is. We should probably read about it. So let's go up. I told you I'm gonna read about it if I ever encounter a question. And out of all these questions, I just encountered one of them. So that probably, yeah, that's why I never actually got in touch with whatever this thing is probably. Because it's not used. It's not, I've not seen this anywhere. Okay, so dispersive power of a lens. Similar to prism, while light on refraction from a lens gets separated into constituent colors, individual components are bent differently. So white ray parallel to principal axis doesn't converge to a point. Rather, there's a spread in the focal length of individual colors. Okay, violet is bent more and red the least. So dispersion is defined as this thing. Dispersive power is, as I thought, it's defined by delta F upon Fy, right? That's what we thought. So, okay, that's understandable. Okay, if two thin lenses are in contact, then the system can be replaced by an equivalent thin lens. Oh yeah, this I'm not interested in that. Okay, this I already know. Oh, now we are going to the thing. When a convex and concave lens of equal focal length are placed in close contact equal. Come on, please don't tell me that. If you want a achromatic combination of the two lenses in contact, you must have delta f is equal to 0. What does that mean? So 1 upon f is equal to 1 upon f1 plus 1 upon f2. What is this? 1 upon f1 squared delta f1? Oh, so you're taking like something like a derivative of this thing. Uh, but art, oh yeah, you're doing 1 upon f squared. So you're taking a derivative with this little wavelength, I guess. Oh, okay, now I understand what we're trying to do. Huh. But is this even correct? Like, is this idea even making sense? Huh? Okay, so delta f is equal to f squared times omega 1 upon. That's the formula that you would use for a. Okay, understandable. Yes, now I understand what. Right. Okay, so delta f upon f, I guess that would be the total dispersive power. Then that's just equal to the dispersive power upon. Okay, it's like, yeah, so you're saying dispersive power total, which is as it's called like WT, and that upon the total focal length, that's just equal to the dispersive power of the first guy upon the focal length of the first guy, and then the dispersive power of the second guy upon the focal length of the second guy, right? That's what you're saying, but is this actually correct? Is this correct to treat it like that? So you want the dispersive power of the uh, of the thing to be 0. Uh, I don't get it. Where's the intuition behind all of these formulae? Why are you defining it the way you're defining it? What does this have to do with dispersion really? Delta F upon, so H upon F is, oh, that's just the deviation. That's not what you look for. Okay. Wait, so think about it. what would happen if you if for some particular ray you just deviated by both of these, right? So your h is not really changing, is it? So you got these two thin lenses and you're going so this is like some ray, I don't know, paraxial, almost paraxial, and then it's just like going like, yeah, its h is not changing throughout the process, so you can just say h upon f1 then plus h upon f2 is the total deviation that ray suffers. Yes. So if this is somehow, and then we know that that's just equal to h upon the total f, right? Now if somehow this deviation is like fixed, so for all wavelengths this deviation is fixed, then yes, what you did is kind of like correct. So just taking a derivative with just to the wavelength, you would get that thing. So really you should actually define your dispersive power as, okay, you actually did define it like that, huh? Fine. Although I don't like that actually. I don't like this kind of definition. Isn't there like a better definition for this thing? I don't know. Okay, so now I understand what condition we're talking about. So each ray of every kind of color deviates by the same angle, right? But does that make sure that these rays will come out as white light? There might be, you know, dispersion without actually having any angular dispersion, you know. So just, yeah, what about that? Won't that happen? You know, it's something like a, it's like two prisms, you know. So it could happen, right? Well, actually, for these two, the white light, this is at least one condition that it should follow, right? So deviation must be the same, otherwise this doesn't make any sense. Now, okay, that's understandable, but actually will it come out as white light or not? Or will it come out as parallel rays of different colors? It could be anything, right? But hey, it's JEE talking about, we don't care about the actual theory. Just deal with the questions, like, this doesn't feel good. Fine. So using this formula, we can get the thing done. Yeah, I don't like this. I really don't like this way of reasoning. But whatever, just deal with it. Okay, so now we can solve the 34th question. Where was it? Right, so dispersive powers is given and then the focal length of one lens is, so once again do the same thing. What is the total dispersive power upon the focal length? So W total upon the total focal length, which is pretty much just like power 1 plus power 2. That's equal to power 1 times the dispersive power of the first guy, which is like W1. So yeah, and then you got P2 omega 2. Yes, yes. So focal lengths are given and whatever, right? What focal length should the other lens have so that they form an achromatic combination? For that to happen, W total should be 0, so this goes away, and that just means W1 upon F1 is equal to negative W2 upon F2 or something. Yes, so F2 is just equal to negative W2 upon W1 F1. Sorry, W1 that times F1, like that. So right, so this is going to be like negative 2 and that times of 10, which is negative 20 centimeters. So it's a diverging length of 20 centimeters. Yes. I think 34th A is the way to go. Yeah. Okay, so now it's done finally. Yeah. Oh, you still didn't do 21. Okay, why did I not do it? Oh yeah, this thing. Accelerated horizontal. That is, I don't know what that means. That's right. One first exercise is just done. So let's check it now. That I'm going to get a lot of wrong questions. But whatever. It's starting, right? So first D, second D, third C, fourth A, fifth C, C A C B, C A C, seventh is C, right? Eighth is B, 9 C, 10 A, 11th A, 12 C. Then you got B C A, 16th D. Oh, it's supposed to be B. Oh. 17 C, 18 D, 19 A, 20 A, 20. Okay, I didn't do 21. 21 B. I don't know. I'll search that later. Okay, 22 C, 23 C D B, 26 D B B A, 30 B B C D. Okay, 34 is wrong. Then A C C. You got B and A. Okay. 38 A. Let's go up. Yeah. Where is it? How many questions are this here? So you are saying A, which is F1, right? So that is, yeah. You know what? No, they are wrong. It's D, right? Yes. So, yep. I mean, like A is just wrong. I can just tell you, like F3 is equal to 0. Makes no sense, you know. Power equal to 0 makes sense. F3 is equal to 0. No, it just won't be like that, right? You have F3 not defined, not that it's 0. That doesn't make any sense, right? It's not just disappearing into 0. No, that's not happening. So 38 is just wrong. Okay, 31st. So they are saying A is not correct, B is correct. What? Suppose that the image must be formed on a card which is at a certain distance behind the lens. While you move the turnip away from the lens, then you should. Huh? No, why should you keep the. If it was already having. Oh, it's not already. Oh, it's that kind of like, you know, how you practically determine the focal length by seeing when an object, so like some kind of lamp or I don't know, when does that actually have its image, a sharp image, right? But you didn't say that you are trying to determine a focal point, right? I mean, you really didn't say that you are trying to determine a focal point. Why should you do? No, it just doesn't make sense. It's just so vague. Yeah, this 31st question I'm giving myself a correct because it was so badly written. They didn't tell me what they want to do. Okay, let's go to 21st. Well, that's just okay. I just don't understand that. Let's go to 16th. Right. So 16th B is the just not correct. You know, you can just see that 16B. Seriously. So in refractive index 1, you have 60 degree as your angle. So okay, just test if that's correct or not. Sine 60 degrees is equal to 3 upon 2, and that times this guy's index, which is just 1. That's equal to sine of 30 degrees, which is like 1 upon 2, and that times this index for 3. Huh? Oh. Uh-oh. Okay. That's where I went wrong. Throughout that, I thought that square root 3 upon 2 is what we should. Oh God. What am I doing? Okay, so this was wrong. I made a mistake over here. Right. It's not that it will just completely no sine 30 degrees 1 upon 2. That's why it was not working. Ah, I feel dumb. Such a small mistake and then it completely ruins everything. Fine. So yes, it's grand. Now I can say that yes, 16th is actually incorrect. Yes, 16th was incorrect. Ah, fine. So the next one. 7th. So 7th A is not correct. C is correct. Two plane mirrors. Okay. Man, M2 is standing there. Once again, the diagram is just so badly given that, yeah, I mean, separated by this L, that's what you said, right? Huh. This thing is L upon 2. Wait, they are separated by this L, okay. Do we know where this guy actually is? So is this like symmetrically separated by L or not? So mirrors of length L, yes. And then they're separated by a distance of L, but that doesn't show in the diagram. I don't know what to make of it. Right? And then how are they separated? So, but yeah, just let's redo it to see if I made some kind of mistake. So just draw the figure once again. I'll draw a big box now. Right? So this is L and 2L, I guess. This thing is L, this thing is L once again. Now, right, this must be L upon 2, this must be L upon 2. And then you got these as L, L. Now, this is the first time this happens. So it's gonna be this whole thing. Like this is 2L times tan of this angle, but then that angle is the same as that angle, right? So tan of this angle is just 1 upon 2. You can clearly see that. So this should just be L, and then that's already L upon 2 up. So it's starting off at, oh no, okay, that's why everything went wrong. Oh, okay, it's starting off at L upon 2 plus L, and then it goes till, so once again, L upon 2 plus. So next time, this is the ray that we deal with. So tan of this angle is going to be uh, 3 upon 2, I guess. So it's going to be 3 upon 2L. Sorry, 3 upon 2 times 2L, so 3L. So L to 3L, you just have 2L of the thing. So the total length is going to be 4L. Even now, it's actually 4L. Right. So 4L and that upon U, that's the time for which it will be able to see it. So why is A not correct and why is C correct? It's 6L upon U. That's as if you have 3L. So, oh yes, like for this particular figure, it might be correct. So you've got L over here, L over here. Boom. Yeah. But okay, that's at the 0. Okay, at 0, you can actually see it. So, and you will also be able to see it when you have L plus 2L. So that's going to be 3L. So for this diagram, it's correct. But then why did it say it's separated by a distance L? Okay, no, these are not separated by distance L. Only then would you get C as the correct thing. And if they are separated by distance L, and in that case, clearly 4L upon U is the answer. Not 6L upon U. 6L upon U will be the answer for this diagram, which is not what the question says it is. I still don't get it. In what way are these separated by distance L? Look, there it is. Their centers. Their centers are separate. Does that? Oh, come on. Ah, you should have told me their centers are separated by distance L. I spent so much time doing. I mean, like trying to solve this stupid question. Their centers are separated by distance L. Okay. Okay. So then, how do we deal with this kind of questions where they don't actually tell you the whole story? What does separation even mean in this context? Does it mean the distance between the edges or between the centers or what? think about it. If two mirrors are like touching at edges, are they separated? No, they're not. But then according to you, these are at separation L because the centers are at separation L. What logic is this? Right. So seventh, no, I'm giving myself a correct. Right. I did all that hard work and now they're just saying it's not correct. It is. It just is. You're just bad at telling questions. So right. That's it, huh? This is it. And final 21st B, which I'll see later. I don't think I know what this question says. So yeah, I'll see you guys in the next video. Bye.